Good morning. So, we are going to discuss today the Bayes decision theory for binary features. So far what we have discussed is assuming that the feature vectors are distributed following some normal distribution of the form P of x given omega I is equal to so this is the expression for a multivariate normal distribution, and we have seen that in this expression where sigma I represents the covariance matrix, that for different conditions of covariance matrices we can have different types of classifier. So, the first case we have discussed is if the covariance matrix for every class I is of the form sigma square into identity matrix I, where both this covariance matrix is of dimension d by d, where our feature vectors are of dimension d, and this identity matrix is also of dimension d by d. So, because this is identity matrix, so this simply says that covariance matrix is a diagonal matrix where every diagonal element is of value sigma square. That means, every component have the same variance, whereas off diagonal elements are equal to 0. So, because off diagonal elements are zeros, so the components, different components of the feature vectors are statistically independent. Okay. So, in such cases we have seen that the classifier is nothing but a linear classifier, or when we talk about the discriminant function, the discriminant function for individual classes, they are also linear functions, and because they are linear functions, so the classifier which employs these linear functions to classify an unknown feature vector, that is a linear machine. Okay. And in particular, if we want to find out the decision boundary between two different classes, the ith class omega I and the jth class omega j, the decision boundary between these two different classes is a hyperplane which is orthogonal to the line joining mu I and mu j, where mu I and mu j's are the centers of the classes omega I and omega j. So, effectively I have a situation something like this, that if I have mu I somewhere over here, which is the mean of the class omega I, and mu j somewhere over here, then the decision surface is orthogonal, is a hyperplane which is orthogonal to the line joining mu I and mu j. Okay. And if the a priori probabilities P of omega I is equal to P of omega j, then this decision boundary or the decision surface becomes an orthogonal bisector of the line joining mu I and mu j. Okay. So, this was our simplest case. In the second case, we have seen that if sigma I is equal to sigma, that is, every class or the samples belonging to every class have the same covariance matrix, but otherwise the covariance matrix is arbitrary. Unlike in the first case where covariance matrix has a specific form like this, in the second case the covariance matrices are arbitrary, but every class have the same covariance matrix, which ideally means that the points belonging to the same class or the points belonging to different classes, they are clustered in hyper ellipsoidal spaces of same shape and same size. Okay. And in such case, we have seen that the discriminating function that we get for different classes, they are also linear. So, in both the cases, in the first case as well as in the second case, the discriminating functions becomes linear. So, the classifier is nothing but a linear machine. However, there is some difference between the decision surfaces that we get between two different classes omega I and omega j. In the first case, the decision surface was orthogonal to the line joining mu I and mu j. In the second case, the decision surface is not in general orthogonal to the line joining mu I and mu j. So, here again, if mu I and mu j, so this is mu I and this is mu j, which are the centers of the two classes omega I and omega j, then the decision surface between these two classes will be something like this. In the previous case, it was orthogonal to the line joining mu I and mu j. In this case, in general, it is not orthogonal. However, the decision surface is a hyperplane or it represents a linear equation. Okay. And here again, if the a priori probabilities p of omega I is same as p of omega j, then this decision surface, though it is not orthogonal to the line joining mu I and mu j, but it will pass through the point which is midway between the points mu I and mu j. Okay. And the third case, we have said that the covariance matrices of different classes are totally arbitrary. Okay. So, for ith class, I will have one covariance matrix, for jth class, I will have another covariance matrix. So, that effectively means that the clusters or the points vectors belonging to different classes, they are clustered into hyper ellipsoidal spaces. In this, in the second case, the hyper ellipsoidal spaces are of same shape and same size. Okay. In this case, the points belonging to different classes will also form hyper ellipsoidal spaces, but these hyper ellipsoidal spaces may not have same shape or may not have same size. So, they will have different shapes as well as different sizes, but the points belonging to the same class, they form an hyper ellipsoidal space. Okay. However, in all these three different cases that we have discussed, we have assumed that the feature vector x is continuous or the individual components of the feature vector x, because our feature vector x is nothing but a d-dimensional vector having the components x 1, x 2 up to x d. So, it is a d-dimensional feature vector. Okay. So, in all these three different cases, our basic assumption was that the feature vectors are continuous, or in other ways individual components are also continuous. That effectively means that if I consider a d-dimensional feature space, then the feature vector can be represented by any point, is represented by any point within that d-dimensional feature space. Okay. I do not have any specific set of points from which the feature vectors are drawn. Okay. However, in most of the practical applications, and particularly these days as we are working with digital computers, so all the data that we get are digital data, and the moment we get digital data, the vectors that we generate are no more continuous, rather they are discrete vectors, or every component of the feature vector, every x I will have discrete values. Discrete values means it will assume one of a set of specific values. So, instead of a continuous variable, it becomes a discrete variable. Okay. So, when it is a discrete variable, in that case, in all our previous lectures, wherever we have talked about integration, the integration is to be replaced by summation, and the summation has to be carried out over the discrete space. Okay. So, we will take a specific case of this discrete feature vectors. Okay. So, let us consider a case where, so we will have our feature vector x, which will be discrete Okay. And we consider a specific case of a 2 class problem. And the feature vectors we will assume to be binary feature vectors. Binary feature vector means every component of the feature vector will assume binary value either 0 or 1. Okay. So, when I have this feature vector x, which is given by x 1, x 2 up to x d, again we assume that we have d dimensional feature vectors. Okay. Every component of the feature vector x 1 or x 2 or x 3 can assume either a value equal to 0 or a value equal to 1. So, that means that if a feature vector is taken from a particular class, it will say whether a particular feature is present or it is absent. Okay. So, when I have this sort of binary feature vectors, we will also assume that different components of these feature vectors are conditionally independent. Okay. To have something similar to statistical independence of different components in continuous feature vectors. So, here also we will assume that different components of the feature vectors are conditionally independent. Okay. So, every feature value in this feature vector x I, every feature value can have a value either 0 or 1. Okay. So, it will say whether the feature is present or the feature is absent, and correspondingly the probabilities will be something like this. So, every feature component will be represented by a probability value, where the probability is something like this, that I will represent p I to represent the probability of the ith component. Okay. So, the p I will be equal to probability that component x I is equal to 1 given that the true state of nature or the true class is class omega 1. Okay. We are considering a 2 class problem. So, we have classes omega 1 and omega 2. Okay. So, p I represents probability that x I is equal to 1 given that the true state of nature is omega 1. Similarly, q I is probability that x I, the same component, is equal to 1 given the true state of nature is omega 2. Okay. So, given this type of probability measures, it simply means that if I have a situation that p I is greater than q I, okay, in such cases it simply means that ith component x I is more likely to have value 1 if x belongs to class omega 1. Okay. Because it is the probability of assuming a value equal to 1, right, when the true state of nature of the true class is omega 1 or when the true state of nature or true class is omega 2. So, if p I is greater than q I, that simply means that if the sample is taken from class omega 1, then it is more likely that the ith component x 1 will have value equal to 1, or x I will have a value equal to 1 more frequently if the vector is taken from class omega 1. Okay. And if it is taken from class omega 2, then it is less frequent that the ith component x I will have a value equal to 1. Is that okay? So, when I have this kind of situation, now let us see that what are the cases in which this kind of feature vectors are more useful. Say for example, if we want to find out the health of a plant, say a power plant, if I want to determine the health of a power plant, then what we normally do is there are a number of sensors which are used to monitor different parameters of the plant, and after monitoring those different parameters, you decide whether the plant is okay or there is some danger in the plant. Okay. And when you monitor the sensor outputs, you just see that whether the sensor output is above a threshold level or below a threshold level. So, if it is above a threshold level, we set a value equal to 1, if it is below a threshold level, we set a value equal to 0. Okay. Or let me take a more obvious example. When you go to the market to purchase oranges, okay, you must have noticed that even in our tech market, you usually get two types of oranges. Okay. One type of orange which are produced at Nagpur, and one type of orange which are coming from Darjeeling. Have you noticed any difference in appearance between these two types of oranges? Color is different. If it is from Darjeeling, color is more attractive. It is really orangey color, right? It is more yellowish. Whereas oranges from Nagpur, they are more greenish, right? And if it becomes quite old, it becomes more reddish. Okay. If you look at the surface texture, the oranges which are coming from Darjeeling, they are smooth, okay, whereas the oranges which are taken from Nagpur, they are rough. Okay. So, if simply based on these two features, I want to determine, I want to have an automated machine which will simply classify, tell me that whether this is a Darjeeling orange or a Nagpur orange. Okay. So, it will try to take that decision based on the color in the simplest case, or it will try to take the decision based on the feature, the texture feature. Okay. So, if I keep some of the feature vectors like whether the color is yellowish, answer will be either yes or no. Okay. Whether it is greenish, answer will be either yes or no. Okay. Whether it is smooth, answer will be either yes or no, right. However, when I get an orange from Darjeeling and I take an orange from Nagpur, there is no guarantee that all the oranges from Darjeeling will always have smooth texture or will always have orangey or yellowish color. Or if I take oranges from Nagpur, there is no guarantee that I will always have greenish color. Nagpur even may produce some oranges which will have a yellowish color or which will have smooth textures, right. So, there is always a finite probability that an orange produced at Nagpur will have yellowish color. Okay. So, it is not necessary if that color to be yellowish, I put that as a binary feature. For all the oranges coming from Nagpur, that binary value will always be equal to 0. It is not guaranteed. For some of them, I may get values which are equal to 1, but that is less frequent than the value equal to 1 when the oranges are taken from Darjeeling. Okay. So, simply over here, if that feature I put as the ith feature x I, okay, then p I will be more frequently equal to 1, x I will be more frequently equal to 1 if this omega I is Darjeeling, okay, and this will be less frequently equal to 1 if omega 2 is from Nagpur. Okay. So, coming over here, if p I is greater than q I, right. So, it simply explains this particular situation, that if for oranges coming from Darjeeling, I will have more number of oranges having yellowish color than the number of oranges I get with yellowish color from the Nagpur oranges. Okay. So, this is a typical situation like this, right. And what does conditional independence mean? The texture and the color, they are independent. I mean, if the texture is rough, that does not necessarily mean that the color will be greenish, or if the texture is smooth, that does not necessarily mean that the color will be yellowish. Okay. So, coming to the plant, if I take two features, say I want to monitor the health of a boiler. If I take two features, one is pressure inside the boiler and temperature inside the boiler, they are not independent, because if temperature increases, the pressure will increase. I mean, just from the basic laws of gas. Okay. So, they are not independent, they are dependent. So, when I try to select the features, I should select in such a way that the features are independent, because that solves many of the mathematical problems. I do not have to look for complicated mathematics. Okay. So, if I assume that the features are conditionally independent, then the same probability function I can write as p of x given omega 1, okay, where x is the feature vector which has d number of binary valued feature components. Okay. So, this p of x given omega 1 I can simply write as p I is the probability that x I equal to 1 given the true state of nature is omega 1. Okay. But it also has a finite probability that it may have a value equal to 0. So, I have to consider that as well. So, it is p I to the power x I into 1 minus p I to the power 1 minus x I. Obviously, if x I equal to 1, 1 minus x I equal to 0, if x I equal to 0, 1 minus x I equal to 1. Okay. And because the components are conditionally independent, so the overall probability will be product of independent probability values. So, this I have to take for I is equal to 1 to d, as I have d number of components. Okay. So, this is the class conditional probability of a feature vector x, okay, if the state of nature is omega 1, right. So, in the same manner I can write p of x given omega 2, that is class conditional probability if the feature vector belongs to class omega 2 is nothing but, now the probability of x I equal to 1 when the true state of nature is omega 2 is q I. So, I will have q I to the power x I into 1 minus q I to the power 1 minus x I. Okay. Take the product from I is equal to 1 to d. D is dimension of the feature vector. So, I have d number of components in the feature vector. Okay. So, these are the two class conditional probability values. Okay. Now, from here I can find out what is called likelihood ratio. So, the likelihood ratio is given by p of x given omega 1 upon p of x given omega 2, which is nothing but, if I simply multiply these two, it becomes p I upon q I to the power x I, okay, into 1 minus p I upon 1 minus q I to the power 1 minus x I. Okay. Take the product over I varying from 1 to d. Okay. So, this is what is the likelihood ratio, right. X I is a single component, it is a scalar. Yeah, X I is a single component. The capital X is the vector, okay, having d number of components. So, but the value of I will vary from 1 to d. Okay. Now, we know that the decision surface or decision function between the two classes, given two classes, is given by g x is equal to log of p x given omega 1 upon p of x given omega 2 plus log of p omega 1 upon p omega 2. This we derived earlier. Okay. Now, if we put this p of x given omega 1 upon p of x given omega 2, which is equal to this expression, if I put this expression into this function, okay, so it will give us, because we are taking logarithm, so the product term over here will be converted to sum of logarithmic functions. Okay. So, what I simply get is g x is equal to summation of x I, because here x y was a power, right. So, this will become a product of the in the logarithmic term. So, it is x I then log of p I upon q I plus 1 minus x I log of 1 minus p I upon 1 minus q I where I will vary from 1 to d plus log of p of omega 1, where this p omega 1 is the a priori probability upon p of omega 2. Okay. So, this is the decision function, and for a two category case we have already seen that if g of x becomes greater than 0, then our decision was that x belongs to class omega 1. If g of x becomes less than 0, then our decision was x belongs to class omega 2. If g of x is equal to 0, that actually tells us that what is the decision boundary between the classes omega 1 and omega 2. Okay. Now, if you notice that this equation is a linear equation, is not it? Because this simply says the linear combinations of different components x I of the feature vector x. I do not have any x I term, x I squared term or x I cube term. Okay. So, the equation is a linear equation, and this linear equation can simply be written in the form, if I just rearrange this particular linear equation, I can write it in the form g x is equal to sum of w I x I plus w 0. Do not confuse w with omega. Okay. So, it becomes sum of w I x I plus w 0, where I varies from 1 to d, because I have d number of components in the feature vector. Okay. So, you find that this is nothing but a linear combination of the different components of the feature vector x I plus a threshold term, which is W 0. Okay. And these W i's for different values of I, this represents a weight vector, and this is nothing but a dot product or inner product of the weight vector with the feature vector. Okay. So, when I write it like this, over here this W I is simply log of P I into 1 minus Q I. That is quite obvious, okay, because you find that this becomes x I into log of P I minus x I into log of 1 plus P I or plus x I into log of 1 minus Q I. Okay. So, this 1 minus Q I term that goes to the numerator and 1 minus P I term that comes to the denominator. Okay. So, it simply becomes log of P I into 1 minus Q I upon log of P I into 1 minus Q I upon Q I into 1 minus P I, okay, where I varies from 1 to d, right, because I have d number of components in the weight vector as well, and W naught, that is the threshold, is given by log of 1 minus P I upon 1 minus Q I, okay. Sum of this for I is equal to 1 to d plus log of P of omega 1 upon P of omega 2. Is that okay? Now, if you analyze this, as I said that our decision will be that if g of x is greater than 0, then we decide that x belongs to class omega 1. If g of x is less than 0, then we decide that x belongs to class omega 2. If this is equal to 0, that is a boundary case. Okay. So, if you analyze this expression, or what do we get? What does these different components of W, that is W I, that effectively tell us? You find that x I, that is the ith component of the feature vector x, is a binary valued feature vector. It can have a value equal to 0, it can have a value equal to 1, right. Now, if it has a value equal to 1, then the contribution of the term W I into x I for that particular component x I to this function g x is nothing but equal to the magnitude of W I, because x I is equal to 1. Okay. So, it is nothing but equal to the value, the magnitude of that particular component of W I, right. So, effectively this W I, magnitude of it, it simply tells you that what is the importance or what is the relevance of the component x I in decision making, that whether the sample will belong to class omega 1 or the sample will belong to class omega 2. If value of W I is very large, then x I has more weightage to decide about the class. If value of W I is small, then x I have less weightage to decide about the class. Okay. And in other case, if P I is equal to Q I, that means value of x I to be equal to 1 is more likely, is same, equally likely, even if the x belongs to class omega 1 or the feature vector x belongs to class omega 2. Okay. So, if p I is equal to q I, p I as we said it is the probability that x I will be equal to 1 if the true state of nature is omega 1, and q I is the probability that x I will be equal to 1 if the true state of nature is omega 2. So, if p I is equal to q I, that simply indicates that whether x belongs to class omega 1 or if x belongs to class omega 2, x I is equally likely to have value equal to 1. So, that simply means that x I has no relevance in deciding the class. So, if x I has no relevance in deciding the class, then why should the corresponding weight w I be there? I can make w I equal to 0 without hampering my decision. Okay. So, if you come to this w I, the expression for this w I, you find that if p I is equal to q I, then this expression p I into 1 minus q I upon q I into 1 minus p I, this expression will be equal to 1, log of this equal to 0. So, the corresponding w I is equal to 0. Okay. And that is quite obvious, because if p I is equal to q I, then x I, the particular feature vector x I, has no relevance in deciding the class of the feature vector x. On the other hand, if p I is greater than q I, okay, if p I is greater than q I, then having value of x I equal to 1 should tell me that the sample is more likely to belong to class omega 1 than to belong to class omega 2, right. Whereas, if p I is less than q I, then the sample x I equal to 1 tells me that it is more likely to belong to class omega 2 than its likelihood to belong to class omega 1. Okay. So, again coming to this particular case, if p I is greater than q I, okay, if p I is greater than q I, then obviously 1 minus q I is greater than 1 minus p I, right. So, in this expression the numerator becomes larger than the denominator. So, this value is greater than 1, and when this value is greater than 1, value of w I is positive. If value of w I is positive, what happens to my g x? Not necessary. It depends upon other values of I as well. Okay. So, effectively I can say that if x I is equal to 1, that particular component, then this component x I gives a vote of value w I to g x to decide that this feature vector x belongs to class omega 1. So, it gives a vote equal to the corresponding weight in favor of class omega 1. Is it okay? On the other hand, if p I is less than q I, p I is less than q I, right. So, 1 minus q I will be less than 1 minus p I. So, numerator becomes less than the denominator. So, this term is a fraction which is less than 1, log of this will be negative. That means, w I in that case is negative. If w I is negative, that means the corresponding x I into w I is trying to make g x less than 0, trying to make, whether it will be less than 0 or not, that depends upon other w I into x I term. Okay. But what x I is trying to do in this case, it is trying to give a vote equal to the modulus of w I in favor of class omega 2, because it is subtracting. So, it is giving a vote which is equal to modulus of w I in favor of class omega 2. Okay. So, if p I is greater than q I, the component x I gives a vote equal to w I in favor of class omega 1. If p I is less than q I, then component x I gives a vote equal to the modulus of w I in favor of class omega 2. Okay. That means, this component is trying to push the decision surface of the decision boundary either towards omega 1 or towards omega 2. Is that okay? Let us take an example. Okay. So, let us consider a 3-dimensional space or 3-dimensional feature vectors. Okay. And let us consider a 2-class problem. That is, I have classes omega 1 and omega 2. So, these are the 2 classes I have, right, and every feature vector is a 3-dimensional feature vector, where every individual component can be either 0 or 1. Okay. And let us also assume that the a priori probabilities p of omega 1 is same as p of omega 2, which is equal to 0.5. Okay. And let us assume that value of p I is equal to 0.8 and q I is equal to say 0.5 for all values of I, that is for I varying from 1, 2 and 3. So, it says that every component of the feature vector has a probability of being equal to 1 is 0.8 if the feature vector is taken from class omega 1, and every component has a probability of 0.5 of being equal to 1 if the feature vector is taken from class omega 2, right. So, given these p I and q I values or probability values, I can compute the corresponding weight vectors. Okay. So, simply from this expression that W I is equal to log of p I into 1 minus q I upon q I into 1 minus p I. Okay. For different values of I get different components of the weight vector W I. So, I get W I is equal to log of p I, that is 0.8 into 1 minus q I, that is 1 minus 0.5, okay, upon q I, that is 0.5 into 1 minus p I, that is 1 minus 0.8. Okay. And if I compute this, this becomes a value 1.3863. Okay. And the threshold W naught, which is given by this expression, W naught is equal to log of 1 minus p I upon 1 minus q I, take the summation for I is equal to 1 to d, plus log of p omega 1 upon p omega 2. Okay. Now, over here in this case p of omega 1 and p of omega 2, they are equal and both equal to 0.5. So, this last term log of p omega 1 upon log of p omega 2, that will be equal to 0. So, what I have to compute is simply this term W naught is equal to log of 1 minus p I upon 1 minus q I, take the summation over I is equal to 1 to d. Okay. So, this W naught will be simply log of 1 minus p I, that is 0.8 upon 1 minus q I, that is 0.5. Okay. This component, take the summation for I is equal to 1 to 3. Okay. And you will find that this value will be something like okay. It will have a value something like this. So, given this, the decision surface between the classes omega 1 and omega 2 you verify these values whether we are truly getting these values or not. So, assuming this, our decision surface G x will be given by sum of 1.3863 x I, where this I varies from 1 to 3, because I have 3 number of components. So, this is nothing but 1.3863 x 1 plus 1.383 x 2 plus 1.383 x 3 minus 1.2, this is equal to 0. Okay. So, if I try to plot this decision surface in 3D, one point you might have noticed that because our features are binary features, okay, every feature component can assume a value either 0 or equal to 1. So, every feature vector will be represented by a vertex of a hypercube in the d-dimensional space. Okay. It can be either 0 0 0 or 0 0 1 or 0 1 0 or 1 0 0 and so on. So, every feature vector will be represented by a vertex in the d-dimensional space of a hypercube. Okay. So, if I try to plot this decision surface, the decision surface will be something like this. So, let us take a cube in this 3-dimensional space. Okay. And if you plot the surface will come out to be something like this. Okay. So, this is our decision surface. Okay. So, you find that this decision surface says that these are the points which lie on one side of the hyperplane, and these are the points which lie on the other side of the hyperplane. Okay. So, it simply says that if at least two vectors of the feature, if at least two components of the feature vector are equal to 1, then the point is classified to class omega 1. Okay.
But sir, it should be at least 1, because equation says if it is at least 1, that means the component is 1, then on it is greater than.
Which one?
The equation for this decision surface that you have just derived.
This one.
Yes, if
Yeah.
at least 1 is.
If at least 1
means 1, then only we can say it is greater than 0.
Oh, right. I mean, it is the other way. These are the points which are put to class omega 1, omega 2, and the other side is put to class omega 1. Okay. So, it says if at least one of them is equal to 1, then the decision will be in favor of class omega 1. Okay. Otherwise, the decision will be in favor of class omega 2. Is that okay? So, you find that I again get a simple hyperplane in 3 dimension, it is just a plane, okay, which is a boundary between the two classes omega 1 and omega 2, right. So, if the probability values are different, if different PIs have different other values, then the position as well as orientation of this plane may be different. But effectively what it does is the entire d dimensional space is broken into two halves. One half will be given to plus omega 1, the other half will be given to plus omega 2. Okay. The nature will be a bit more complicated when the number of classes are more than 2, because then we have to think of more than one decision surfaces and how they combine. Okay. Axis represents x 1, x 2, x 3, right. Okay. So, let us stop here today. Thank you.